Assignment in this lecture is to talk about relativistic magnetohydrodynamics, and I'll try and give you a sense for those of you who are not working in relativistic astrophysics at the moment. I'll try and give you a sense for what the basic equations are and how they're solved, and what variables we use to describe a relativistic magnetized fluid. And then I'll talk about codes and code tests, and I'll wind up with a little discussion of where the field is going next and sort of beyond ideal MHD. And before I go to that, is Jim here? Maybe not yet. So this is for him, actually. So I just want to point out that it is possible to do problems in which the radiation pressure is significant, although perhaps not dominant, with a Monte Carlo radiation MHD code. There he is. Okay. Someone went and got him. So this is a shock tube test that we've done with a code called Blight. And Blight combines a relativistic MHD code with a relativistic Monte Carlo radiation transport code. And this is sort of the simplest way, although, as Jim pointed out, an extremely expensive way of getting at the dynamics of a relativistic radiating plasma. And there's two lines here. There's a red line, which shows the output of our Blight code. And then there's a dashed line, which is an approximate solution for the structure of this radiating shock that's obtained in a type of diffusion approximation. And that's from work by Brian Ferris and Shapiro group. Okay, so I just wanted to offer that as a coda to Jim's talk. Okay, so here's the plan. Talk about when relativistic MHD is required, because if you don't have to do relativistic MHD, so for example, you're working on a black hole accretion problem, but you're interested in the disk far from the event horizon, then you shouldn't do relativistic MHD, because it's very expensive. It's factors of 3 to 5 or more expensive than non-relativistic MHD. So then I'll talk about basic equations, the fundamental variables in the problem, and a little bit about conserved currents, so energy and angular momentum fluxes. And then come back to some numerical techniques and dirty secrets, and finally beyond ideal MHD. So the next stage I'm going to do on the blackboard. So if we could kill the projector. Okay, so the first question I want to answer for you is when do we need to do solve the equations of relativistic MHD? And the first situation, am I writing large enough for those of you in the back? Can you see it? Okay. Is when one of the wave speeds, one of the characteristic speeds, is of order the speed of light. And the characteristic speeds of interest here are the velocity of the plasma, the Alfvén velocity, and the sound speed. Okay, So let's start with the sound speed. If we have a so-called gamma law equation of state, in which the pressure is proportional to the internal energy per unit volume, then we can write for the non-relativistic sound speed what is hopefully a very familiar expression, just gamma p on rho. This is the adiabatic sound speed. And this is sort of the ratio of the restoring force per unit volume to the inertia per unit volume. And you can see that in the limit where either the pressure becomes very large or the density becomes very small, this can become large. And in that case, starting from the equations of relativistic hydro and then doing a linear analysis, it's possible to show that the relativistic sound speed is then gamma p over rho, it's gamma over gamma minus 1, p over c squared. Okay, so what we've done is we have the same restoring force per unit volume, but now the pressure of the fluid is included in the inertia. And this can be rewritten in the form relativistic. So that means relativistic Okay, so you can see that as the non-relativistic sound speed, let's see, no, I've got an extra factor in there. As the non-relativistic sound speed approaches the speed of light, this factor comes in and starts to save you. And for a fully relativistic fluid, we expect that gamma is equal to 4/3. So this is, rho is 3p. And in that case, in the limit where the non-relativistic sound speed is very large, this goes over to c squared over 3. Okay, so I think it's easy to see that that's the asymptotic limit. Okay, so this sound speed is directly related to the temperature of the gas. And if we assume that we can still use an ideal fluid equation of state, where n is the number density, Boltzmann, and temperature, and the number density is the rest mass density divided by the rest mass per particle, then P of order rho c squared implies that kT over mc squared is about 1. So in other words, the temperature in units of the rest mass is of order unity. Okay, so it's common to define in this business certain dimensionless temperatures. So people write theta for some component I is k T for that component divided by mic squared. And for electrons, theta E equal to 1 corresponds to 5.93 times 10 to the 9 Kelvin. And for theta P equal to 1, the temperature in more recognizable units is about 10 to the 13 Kelvin. Okay, so this condition is commonly met in models of relativistic plasmas close to accreting black holes when the accretion rate is low. All right, so the next wave speed was the Alfvén speed. And as you learned at your mother's knee, the Alfvén speed is b over root 4 pi rho. So this might be in Gauss. And obviously, as the density goes to 0, the Alfvén speed diverges. And you're saved, as you can sort of guess, in the relativistic case by replacing density in the denominator, which represents the inertia of the plasma, by density plus something that accounts for the inertia of the magnetic field itself. Okay. And this is just the non-relativistic Alfvén speed over the square root of 1 plus the square of the ratio of the non-relativistic Alfvén speed to the speed of light. Okay, so as the non-relativistic Alfvén speed goes to infinity, the relativistic speed goes over to the speed of light. Okay, and the dimensionless parameter that describes this is the ratio of these two terms, which is commonly called sigma. And this is b squared over 4 pi rho c squared, which is the ratio of the energy density of the magnetic field to the rest mass energy density. Okay, and then finally we need relativistic hydro. I mean, it's obvious that we need it when the velocities in some relevant frame are comparable to the speed of light, but we also need it when the geometry is non-trivial. So one way of putting this is that the gravitational potential in Newtonian form is comparable to speed of light squared. Okay. So if these conditions are satisfied, and you think that a relativistic fluid approximation might be a good approximation to the behavior of the plasma, which in many cases is not at all obvious, then you may want to go and use a relativistic fluid model. Okay, so on to the basic equations of relativistic MHD. So we're going to write and integrate the equations in conservative form. So I'm going to write this like this. Okay, and the fancy letters indicate that, of course, this is a vector, and that there's a list, basically, of conserved quantities that we're going to push forward in time, and corresponding fluxes and source terms. Okay, so it's just like non-relativistic MHD, but we need to be careful with what we mean by conserved quantities and what we mean by this derivative operator. Okay. So what I'm going to do is go through and write down each of the basic equations in non-relativistic form, and then use that to motivate a transformation to, with sort of a replacement rule, to a relativistic form, which looks extremely similar. Okay, so the mass conservation equation in non-relativistic form is that. And then in Cartesian coordinates, you can write this like this. And so this is a component notation that Landau and Lifshitz use. And there's a summation rule here over the indices. All right. So the relativistic equivalent of this looks like this. Okay, so what's new here is that we've introduced the 4 velocity u mu, and u mu is the rate of change of some coordinate x mu with respect to a clock that's carried by an observer that's moving with that speed. Okay, so this is the so-called proper time. So we've introduced u mu. We have to define density a little bit carefully. Density here is really related to particle number density. That's the conserved quantity here. And it's particle number density measured in the frame co-moving with the plasma. And finally, I've used this thing, which is the covariant derivative. And I'm pretty sure that this is not the place for you to learn about covariant derivatives. So what I'm going to do is just show you how this derivative operator expands out in each of the equations of interest. Okay. So just to make sure we're on the same page here, in Cartesian coordinates in flat space, this 4 velocity, as I think most of you know, is okay. So gamma here is the Lorentz factor. And I've now gone over to setting the speed of light equal to 1. Okay. So obviously, the components of the 4 velocity are not independent. There are 3 independent components. And the 4th is obtained by a normalization condition. And the normalization condition is written like this. So in the relativistic equations, will matter when the index is up and down. And as many of you know, I hope, the index can be raised and lowered using the metric. Okay, so you hit, okay. There's some people that are saying, you're telling me something that I learned 5 years ago, and others who have not seen this before, I'm sure. Okay. All right, so that equation can be expanded out in a coordinate basis in the following form. Okay, so this del I means partial xi. And that is just an ordinary partial derivative. And this is true in any coordinate system. So root minus g here is gives the geometry. And g is defined to be the determinant of the metric with the indices down. Okay, so just to remind you, in Minkowski space, in spherical coordinates, the metric with indices down, so this is t, r, theta, phi. The metric with indices down is diagonal and looks like this. And so the determinant minus the determinant of the metric, root minus g, becomes r squared sine theta. Okay. Okay, so notice that our conserved density of particles is now root minus g times the density in the plasma rest frame multiplied by something like the Lorentz factor. So this conserved quantity is coupled in with the velocity of the plasma. Okay, so ultimately what we're going to do, what everybody I think does numerically, is to push the conserved quantities forward in time using a finite volume method, and then solve from the full set of conserved quantities for a set of primitive variables that are more closely related to recognizable physical quantities. Okay. So on to energy momentum conservation. So in the non-relativistic context, this can be written for the conservation equation for the total energy, has same form, d by dt of energy density is minus the divergence of an energy flux. Okay, so everybody knows this. So there's bulk transport of kinetic energy here, transport of internal energy plus PdV work here, and then the Poynting flux over here. Okay, so then the momentum equation looks like this. Where pi ij is the stress tensor. So the stress tensor describes transport of I momentum in the j direction, the flux of I momentum in the j direction. And the stress tensor looks like this. Okay, and that's it. So there's bulk transport of momentum, gas, and magnetic pressure, and then this off diagonal term that ultimately gives you the terms corresponding to magnetic tension. Okay, and that's the full non-relativistic form. So in the I think I have to erase. So in the relativistic case, these two equations are combined. and they take on a very simple form. And the simple form is this. Okay, where T mu nu is now second rank, four-dimensional tensor of a 4x4 matrix. And again, this is the covariant derivative. So all the physics is in here in the stress energy tensor. And this equation can be expanded, or the covariant derivative can be expanded in a coordinate basis in this form. So the components of the stress energy tensor, the time components, give the conserved quantities, and then the the space-time and space-space components give the fluxes. And then there's an additional term here that arises from the covariant derivative. And I hope I have my signs right. Where the covariant derivative is multiplied by something called the connection. Which is proportional to derivatives of the metric. Okay? And this thing includes all the geometry terms. So it includes the effects of the gravitational field. And if you're working in a rotating frame, for example, it includes the effects of the Coriolis force. It includes the effects of centrifugal force. Okay. So now, to go further, we need to specify the stress energy tensor. And the ideal MHD stress energy tensor is written like this. And I'm going to need to erase again. Okay, so the new variable here is this 4 vector, b mu. And b mu is easy to interpret because it reduces to in a frame co-moving with the plasma in a Cartesian coordinate basis, it reduces to the components of the ordinary magnetic field. So it's the field you would measure with a magnetometer in the frame of the plasma. Okay. And then it transforms like a tensor so that immediately tells you how to obtain the components in other frames. You just boost this. If you're working in special relativity, you can boost that plasma frame value into any other frame. Okay. So in the fluid frame, so FF means fluid frame here. This tensor looks like this: rho plus u plus p squared over 2. So this entry, this time entry, in the stress energy tensor in the fluid frame can be interpreted as the energy density. Okay. And then there are additional terms. And I'm going to orient this so the magnetic field is pointing along the third axis. And then these terms reduce to pressure plus b squared over 2. And the final entry is pressure minus b squared over 2 in the direction pointing along the magnetic field. Okay. Okay, so again in the plasma frame, b mu reduces, the space components reduce to the ordinary components of the magnetic field that you would measure with a measuring device, and the time component is 0. Okay. So there's a constraint on this 4 vector that b mu dot u mu, which allows you to pick out the time component in the plasma frame. So that's what this does. So I take the dot product of this 4 vector with the 4 velocity, picks out the time component. That vector, that component has to be 0. Okay, so what that tells you is that there are 3 degrees of freedom in this 4 vector, and then in addition, this constraint. So we have the same number of degrees of freedom in the relativistic case as in the non-relativistic case. Okay. And then the other new feature of the relativistic form is that instead of having rho VV, here we have rho representing the inertia of the fluid plus terms connected to the temperature of the plasma. So we're taking account of the inertia associated with the internal energy of the plasma and the inertia associated with the magnetic field. Okay, so that's where that enters. Okay, so on to magnetic field evolution. Here, in the non-relativistic case, again, everybody learned the induction equation. In this form. And most of you probably know that this can be rewritten in conservative form as del I Vj Okay, so has everybody seen this before? Yes, yes, okay, thank you. Okay, so the relativistic form of this equation is very similar to this. As you might guess, we just promote the divergence operator to a covariant derivative. We promote the velocities to 4 velocities, and we promote the components of the magnetic field to this B 4 vector. So that turns out to look like this. Okay, and then this can be expanded in a coordinate basis. Into this form using an identity. Okay, so then it's convenient to define a new variable which is related to the time component here. And that will define as b tilde I, and that's just bi ut minus ui bt. Okay, so this is the so-called primitive variable that's used in evolving the equations. This is the basic representation for the magnetic field. And so then we substitute that in here. To obtain an evolution equation for b tilde. Yes, I've got my indices in the right place. All right, so you'll see that this gives us 3 equations. So for each of the spatial components I is equal to 1, 2, 3, x, y, z, r theta phi. There's a fourth component, the time component of the equation, which reduces to the no monopoles constraint. So the fourth component looks like this. And that's the relativistic manifestation of the no monopoles constraint. Okay, so that finishes the discussion of the basic equations. You can see that the form is very, very similar to the non-relativistic form of the MHD equations. It can be written in conservative form, the new variables that we've had to introduce are the 4 velocity and the magnetic field 4 vector. Okay. So when we evolve these in time, we have to evolve the conserved variables, which again are root minus g rho ut for the density, root minus g rho plus u plus p plus b squared ut for the energy and momentum, plus p plus b squared over 2 gtt minus bt for the energy and momentum, and then for the magnetic field, root minus g b tilde. Okay, so these are the things that we can push forward in time, and they're nonlinear functions of the primitive variables, which I will list below here. And those are simply the rest mass density measured in the plasma frame, the internal energy, again, measured in the plasma frame, the magnetic field components, and then the space components of the 4 velocity. Okay, so space components of the 4 velocity contain all the information that you need to evolve the system, but they're inconvenient because, for example, in black hole ergosphere, these component values don't range from -infinity to infinity. Okay, so there's a hard limit on the azimuthal velocity, for example, inside a black hole ergosphere, because the plasma cannot be stationary in the frame of an observer at infinity. Okay? So it's better to use variables that range from -infinity to infinity, so that when we do interpolation and reconstruction, truncation error doesn't lead to non-physical values. And so we use something which I'll denote U tilde, which is the spatial components of the 4 velocity projected into the frame of what's called the normal observer. So the normal observer is guaranteed to be a physical observer, and it's the 4 velocity in which the space components of the 4 velocity are 0 in a coordinate frame when the indices are down. Okay. So this has the advantage that ui tilde ranges from -infinity to +infinity. So it's a good set of variables. Okay. So on to conserved currents. if you're dealing with a non-dynamical space-time, so you're integrating fluid in a non-dynamical space-time, then your metric probably has certain symmetries. So in the case of the Kerr metric, axisymmetry or time translation symmetry. And those symmetries give rise to conserved quantities. So again, as an example, in the Kerr metric, which we might coordinatize with Boyer-Lindquist coordinates, t, r, theta, phi, so colatitude, radius, longitude. The axisymmetry implies that the phi derivatives of the metric are 0, and stationarity, or time translation symmetry, implies that del t is 0. Okay, so let me give you sort of an abbreviated discussion of the way these symmetries are represented. So they're represented using so-called killing vectors. And if there's a symmetry related to an ignorable coordinate like phi or t, in other words, del phi is 0 or del t is 0, then you can write down a so-called killing vector. So let me write it this way. So partial derivative with respect to some coordinate is 0, implies the existence of a killing vector in which that component is, say, 1, and all other components of the vector are 0. Okay, and this killing vector obeys something called Killing's equations, which look like this. You'll see why I'm doing this in just a moment. Okay, so that's Killing's equation, and again, those are covariant derivatives. So this tells you that if you interchange these two indices, you change the sign of the derivative of the Killing vector. Okay, so in the Kerr metric, this is a Killing vector where this index is t, r, theta, phi. And that's the time-like Killing vector. And then there's a toroidal Killing vector, which looks like that. Okay. So it turns out that this leads to a conserved current. And the conserved current looks like this. Okay, so I just take the dot product of the stress energy tensor with a Killing vector. And that gives me a conserved current J mu with del mu J mu equal to 0. Okay, so that's what I mean by a conserved current. So let's just evaluate this and show that this is true. This takes 2 lines. Okay, so the covariant derivative acting here is 0. And so we're left with this. Okay, and I'm freely moving indices up or down. I can do that. I can switch them up and down. This is symmetric under interchange of indices. And this is antisymmetric under interchange of indices by Killing's equation. And so that product must be 0. Okay, so this is 0. Okay, so what are the implications of that for our integration of the MHD equations? The implications of this are that the source terms on the right-hand side of the equation, the connection dotted with the stress energy tensor, vanish for the time and phi component of the equations of motion, so the energy and the angular momentum components, in the Kerr metric. And likewise, if you're studying a problem in a different metric with a different symmetry, there's an associated conserved current and associated source terms vanish. Okay. All right, so I think I'm almost done with this section. So on to numerical techniques. Okay, so it's, as Jim said in his lecture, MHD, numerical MHD is becoming pretty mature. And there are now, I think, more than a dozen codes to integrate the equations of relativistic MHD. And most of those codes are available, publicly available online. So I can think of the Whiskey code, Athena++ now, Chris White's code, Luca Delzana's Echo code. There's a code out of the relativity group at Illinois called the Illinois GRMHD that Zach H.N. has played a role in writing, and that's includes a dynamical space-time. And by the way, just to give you a sense for how expensive the relativistic MHD is, in that code, the MHD sector dominates the gravity sector in terms of computational expense by a fairly large factor. So it's easier, computationally easier, to integrate the Einstein's equations than to integrate equations of relativistic MHD, although not conceptually simpler. There's also a special relativistic version of Pluto, the harm code, which some of you used on Monday. There's a code called GR Hydro. There's a Kyoto group code, Masaru Shibata's group, and an LSU group code. So I'm going to give you a few comments about how these integrations are done based on our own code, harm. And I'm going to focus on the pieces that are different from non-relativistic MHD. Okay, so the idea, as in non-relativistic MHD, is to start in each zone at time step n with a set of primitive variables, and then transform these through a set of nonlinear but analytic operations into a set of conserved variables. And then step these forward in time using your favorite technique. So something happens in here, say a finite volume method. In our case, we use a second order scheme, and we use very simple fluxes. We use local Lax-Friedrich fluxes, and I'll show you some of the problems with that in a minute. And we step that forward to time step n+1 using that second order scheme. And then at the end of the day, we have to invert and obtain the primitive variables from the conserved variables. And that operation is not analytic. It requires numerical solution of a set of nonlinear equations, one or more nonlinear equations. Okay. So again, just in harm, we use, we have no solution of Riemann problem. Or, so this is local Lax-Friedrich. And for that, we only need to estimate the fastest wave speeds. Okay, so Harm uses a particularly quick and dirty method for estimating the fastest wave speeds. And our estimates are approximate. and they deviate from the exact fastest wave speeds only when the ratio of the alphane speed to the sound speed is 1, or close to 1. Okay, so local X Friedrich is diffusive in comparison to more sophisticated techniques, say Athena++. But it's also simple. So I think we designed the code in what Jim described as the wrong way, where we were seeking to get it right first and then maybe later make it fast. So this is complicated enough, I think, without optimization. Okay, and then finally, as in the non-relativistic case, we still need to maintain the constraint divergence B is equal to 0. So I'm not sure what you've heard about this already, but there are a few possible approaches that one can try. So the first approach that people tried 3 decades ago is to hope for the best. So you start up your code and you make no special provisions for keeping divergence B as 0, and it's pretty clear that fails. And it fails because the monopole density random walks away from 0 at best, with a step size that is of order the truncation error in the code. And so that grows and grows over the course of the simulation, then eventually everything comes to a tragic halt. Okay, the second method is to use constrained transport, and that embeds this constraint into the evolution procedure for the magnetic field. And that's what we use in HARM. This is a method used by discriminating numericists everywhere. And in this case, the monopole density still random walks away from 0, but it random walks away with a step size of order round-off error rather than truncation error. Okay, so another approach which Alindo uses is divergence cleaning. So you can periodically, during your evolution, solve for the nearest magnetic field configuration to the numerical field configuration, which has 0 monopole density. And that involves solving an elliptic equation. Okay. And then the final approach is to evolve an additional field. This is the so-called hyperbolic divergence cleaning approach. Evolve an additional field which causes, through an additional term in the induction equation, causes the monopole density to relax to 0 over time. And that's the so-called Dedner et al. Approach. So let me just list these. Hope for best. No. A constrained transport. Clean up after yourself. Relax to clean up. And then the final approach, which is used in the Illinois GRMHD code, so that's the Shapiro group code, is to evolve the vector potential. And then you take a derivative of the vector potential to get the magnetic field, and that's guaranteed to be divergence-free. Okay. So, so again, this all applies to the non-relativistic case. HARM and most relativistic MHD codes use constrained transport. The distinctive feature, really, of the relativistic MHD is that this process is no longer analytic. And I think it's now fairly well understood how to do this. There are good procedures for inverting the variables. And it's understood that the errors incurred in these numerical procedures do not dominate the errors in the evolution. And it's if the method is implemented appropriately. And it's understood that this inversion operation need not dominate the computational cost of the scheme. Okay, so yeah, question?
So the primitive variable step is only to estimate the wave speed?
No, I'm sorry, I maybe said that in a way that was misleading. No, so in order to calculate the fluxes, we need to start with the primitive variables. So at the end of every time step, we need to, and actually in our case, twice per time step, we need to recover the primitive variables and then use those to calculate the fluxes. So there is no analytic operation that takes us from the conserved variables to the fluxes. So if there were, we could dispense with the primitive variables altogether in the course of the evolution. Yeah.
How come we have to treat divergence of B differently? So we have other conserved quantities, and we don't seem to worry about energy decay or whatever.
Well, so this is a differential constraint on a single time slice. So the other conserved quantities, so the conservation of, say, mass is built into the basic evolution. So any mass that's handed out of one zone is captured by the next.
I see. So you can just like integrate them out because it's not different.
Well, the conservation is built into the equations, built into the numerical evolution in this case, because we've written things in a conservative form. It's of course possible to write the equations and integrate them in non-conservative form, but that leads to problems with the behavior of the solution in shocks, say. Okay, so this is distinctive in that it is a constraint that's imposed on a single time slice, and then the maintenance of that condition is guaranteed analytically by the evolution equations, but it's not guaranteed exactly by the difference equations unless you use constrained transport. Okay, so a couple of notes on dirty little secrets. One problem that's common to relativistic MHD and non-relativistic MHD is that sometimes the evolution takes these conserved variables to non-physical values. So for example, the conserved density may become negative. And to prevent this, most codes impose constraints on the solution. So you finish your time step and inspect the values of the density, and you find a negative density, and then you go in and you impose what's called a floor, which simply involves moving that negative value back to a respectable positive value. Now, why on earth would I be allowed to do this? Because I'm not actually solving the equations. Well, it turns out that this happens only in certain extreme parts of the flow. So in regions with very low density and frequently regions with very high magnetic field strength. And in that case, the amount of mass involved is small compared to the total mass of plasma on the grid. And so when I make this change, I don't make a significant change to the global evolution. And this is something that you can check by varying the fix-up procedure, varying the amount of mass you add in, and so on. Okay, so harm imposes the following conditions. Density is larger than a minimum density. Internal energy is larger than some minimum internal energy. And the Lorentz factor, as measured by the normal observer, okay, so here's the normal observer for velocity, here's the plasma for velocity. minus the dot product is the Lorentz factor of the plasma in the normal observer frame. This has to be smaller than some maximum Lorentz factor. Okay, and if it isn't, then we rescale our velocity components until it is. And again, this tends to occur in regions of the flow where the magnetic energy density dominates the internal energy density and even the rest mass energy density. So regions where the parameter sigma, which I defined here, is large compared to 1. Okay, so in the course of this fix-up, one introduces errors into the density and temperature evolution, and I think that's just a fact of life. Because we're integrating an energy-conserving method that conserves the total energy, which is the sum of all the energy components, we inevitably make truncation errors in the total energy. And so when we try to extract small components from that, like the internal energy, we can make large order unity or larger errors. And there doesn't seem to be a good way around that. Okay, so I'm done with that piece. Okay, so I just wanted to talk for a couple of minutes about code tests. And I'm going to start with a sort of credo, which is due to Feynman. And Feynman says the first principle is that you must not fool yourself, and you are the easiest person to fool. So my graduate students come to me all the time and they say, well, we're doing this test problem, but it's not giving the right answer, but I'm sure the code is right. And I have enormous respect for my graduate students. Everybody goes through this phase. And then Feynman also says, I'm talking about a specific kind of integrity in science, an extra type of integrity that is not lying. It's not lying, but it's bending over backwards to show how your work may be wrong. And I think we're particularly obligated to do that in situations where we're presenting numerical results, where we're more familiar with the techniques than the reader may be. Okay, so this shows a quantitative convergence test of a relativistic MHD code. And this is from the Harm paper. So this is an Alfvén wave test problem. You set up a grid and insert an Alfvén wave, and you compare the numerical solution to the analytic solution and take the L1 norm of the difference between the two. And this shows, these straight lines show second order convergence. And you can see that once the resolution is high enough, Harm gives good second order convergence. So this is very reassuring. Okay, but this is a linear problem, and it doesn't exercise the nonlinear terms in the basic equations. So this shows an additional nonlinear test problem where we integrated this classic MHD test called the Orszag-Tang vortex, which is a test problem that produces shock waves and produces a current sheet in the middle of the grid. And we compared the solution from Harm to the solution from a code which we believed was correct because it was written by one of our co-authors, called the versatile advection code. And this shows both solutions in a cut across this two-dimensional test problem. And here we're just looking at the density. It shows both solutions plotted on top of each other, and you can see that they're very, very close. And this shows 4 times the difference. So we sort of bent over backwards to show how our solution might be wrong. And you can see that there are some small differences, particularly in the way the two codes treat the discontinuities, but otherwise it looks pretty good. Okay, and we can do a more quantitative test and see that of the same, this is again the Orszag-Tang vortex, and now we again take L1 norm of the difference between the two solutions over the entire grid and increase the resolution on this axis. And this shows first order convergence, and the codes do converge at first order, as we expect, because this is a flow with discontinuities in it. Okay. Okay. And then one wants to also test the code in some application which is close to the intended application, but analytic. And this shows harm performance on a relativistic test problem, which is analogous to the Weber-Davis solar wind solution. Okay, so that's a one-dimensional solution for a magnetized solar wind. And this is similar, but we've turned it inside out and used it to describe flow from the innermost stable circular orbit in the equatorial plane of a black hole in through the event horizon. So this has the full non-trivial space-time in it. And again, we get second order convergence. So we think the code is working. Now, working on smooth problems isn't everything. So now I'm going to expose some more dirty laundry. So this is the so-called field loop advection test. This has a vector potential which looks like a dunce cap. And it corresponds to a loop of field with constant magnitude that then ends suddenly. So there's a sudden feature. And this shows, here the color shows b squared. Okay, so we advect this field loop across the grid with harm. And that doesn't look very good. So there's a significant dispersion error associated with our numerical technique, which can be traced to the way we evolved the magnetic field, and in particular to the way in which we've implemented constrained transport. So the sort of shorthand description of this is that we don't upwind the EMFs. So I think Jim designed the test specifically to show that. Sorry?
Not in your code.
Yeah. No. Okay. So this shows J squared, which is related, of course, to derivatives of the magnetic field in the same test problem. And again, we advected across the grid, and you can see there's significant dispersion error. Okay, so here is the same J squared with Athena. So here's Jim showing off. And that looks pretty good, actually. So if the application you're working on requires that you capture these discontinuities in the magnetic field with little dispersion error, then you should use Athena. But I just want to say, in my own defense, if you do the same problem without the sharp edges, so you consider advection of a smooth magnetic field configuration. So this uses a vertical component of the vector potential, which looks like a Gaussian, which corresponds to a smoothly decaying ring of magnetic field. Then we do fine, and the result is convergent. Okay. And likewise for the current in the same problem. There's a feature there which is associated with the initial conditions, but would go away in a larger grid. Okay. Okay, so I want to show you one additional problem, test problem, which shows how harm fails when this sigma parameter is large. And this is one of Komisarov's sadistic explosion problems. So anybody who's working, any of you who are working in relativistic MHD have tried this. So we have a region which is highly overpressured in the center of a periodic box, and we put in a uniform magnetic field on top of that, and then let it go. I feel I could hypnotize the audience. Okay, so what's the problem here? The problem is what happens behind this fast shock. Okay, so this is a region with very low density and very high magnetic field strength. And in that region, harm just fails. And so we have to go in and do these fix-ups. And the fix-ups produce noise in the solution. So if you need to get this piece of the solution correct, again, you may just be in trouble. I'm not sure that there's any method that can do this scheme well. In fact, I don't know if I can say this on the record, but there's a strong field version of this, which Komisarov's code successfully solved in his 1999 paper. And I went back to him afterwards to ask for the solution, and he said he couldn't reproduce it anymore. He forgot how he had done it.
He told the same to me.
What's that? He told the same to you? Okay, so that's, okay. Okay. Okay, so I just wanted to spend a few minutes talking about where one might go beyond ideal MHD. And I'm going to describe a little bit of work we've done that's motivated by the problem of low accretion rates, low accretion rate accretion onto spinning black holes, and in particular by the upcoming Event Horizon Telescope observations of the galactic center and of M87. Okay, so there was a presumption that was built in at the beginning of this discussion that the fluid approximation was a good place to start. And usually we think that the fluid approximation applies when the mean free path of a particle to particle-particle scattering is small compared to the size of the system. And the way of describing that in terms of dimensionless numbers is, again, it's called the Knudsen number, the ratio of the mean free path to the size of the system. And in systems like the galactic center accretion flow, this parameter is not small compared to 1, it's large compared to 1. So electrons have a mean free path to Coulomb scattering along the magnetic field, because they are tied to field lines, which is of order 10 to the 5 times the horizon scale. Okay, so the mean free path for Coulomb scattering by ions and electrons is large compared to GM over c squared. But the effective mean free path perpendicular to the field lines, which is set by the gyro radius of the ions and electrons, is still small compared to 1. Okay, so if the mean free path is large, you might think that, I'll just use this as a pointer. You might think that the associated viscosity, which is usually written as the thermal velocity or the sound speed multiplied by the mean free path, would be large, and that the viscosity might play a significant role in the evolution. Microscopic viscosity. So, for those of you working in disk theory, the first thing that you learn is that microscopic viscosity is small, and that you have to resort to some sort of turbulent transport of momentum, angular momentum. Whereas in these flows, viscosity might be large and provide a non-trivial amount of transport. Set that down. Okay, so this leads to a couple of observations. So the first is that the viscosity that's present is likely to be anisotropic. So particles can carry momentum along field lines, but not perpendicular to field lines because they're constrained by their gyro orbits. We will also have not just momentum transport, but also energy transport along field lines, so thermal conduction. And finally, because the Coulomb scattering is so inefficient, it's possible to decouple the electrons and the ions. So it's possible that they have well, first of all, it's possible they have non-thermal distribution functions in each component, but the amount of energy in each of those components may be distinct. They may have different temperatures. Okay, so there's a group of us who have been working to build models that address these observations, that incorporate these observations. And one result, which includes the viscosity and the conduction, is a theory called covariant extended MHD, in a paper written by my student Mani Chandra, François Foucard, and others. And then a theory that incorporates the possibility that the electrons have a distinct thermodynamic evolution from the ions. And that's work that was led by Sean Ressler, who is here somewhere. Sean, good. Okay, good. Okay, so I'm just going to talk a little bit about the extended MHD model. And the idea here is to start with a fluid description and then try and make corrections to the fluid description that account for the viscosity and thermal conduction. And this amounts to adding some additional terms into the stress energy tensor. And then also defining a couple of new dependent variables, which we evolve in addition to the usual fluid dependent variables. Okay, so in this model, I won't use that again, this covariant extended MHD model, we include a heat flux, which is only allowed to run parallel to the magnetic field lines. So this is just like the anisotropic conduction that's implemented in Athena, but we've done it in a slightly different way, as I'll explain in a moment. So here I've switched notations a little bit, and this is the magnetic field 4 vector, but this is a unit vector. Okay, so it tells us what direction the field is pointing in. And we can say that the heat flux is some scalar quantity multiplied by that vector. So that tells us the direction of the heat flux. And then we have the possibility of momentum transport parallel to the field. And that's incorporated in a stress energy tensor that looks like this, which those of you who are non-relativistic plasma physicists will recognize as looking like the pressure tensor from Brzezinski theory. Okay. So viscosity produces a deformation of the distribution function in momentum space. And if there's no magnetic field present, that deformation can change the distribution from being spherical in momentum space to being triaxial. Okay? And there's a relativistic theory that describes that that's called Israel-Stewart theory. Once you introduce a magnetic field, the two directions perpendicular to the magnetic field lines have to have similar distributions of perpendicular momentum. And so we can then describe the distribution function according to the pressure difference, the velocity dispersion difference between the direction parallel to the field and perpendicular to the field. And that is this scalar quantity delta P here. And so that leads to this definition for the stress energy tensor, which includes sort of a projection operator parallel to the field lines, and then a projection operator here, which makes sure that these stresses exist only in the hyperspace perpendicular to the 4 velocity. Okay, so it's the space components rather than time. We don't want to introduce any time components here. So, so this will go over to the Brzezinski stress tensor. Okay, so it's possible to just write up this theory in a very naive way, and that's what people did in the 1950s and in the 1970s. And the naive theory, in which, for example, one sets the heat flux proportional to the gradient of the temperature plus a relativistic correction. So this is the 4 acceleration of the fluid, and this is what comes out in what's called the Eckhart theory. Okay, so now the heat flux has a component which is proportional to the 4 acceleration. And this is required, by the way, to get the temperature distribution right in the presence of a gravitational field. So conduction in the present, without a gravitational field, tends to bring the temperature to a constant. Okay, but conduction in the presence of a gravitational field tends to bring the redshifted temperature to a constant. And this term introduces the correct redshift. Okay, so if you write down this naive theory, then you find that it's unstable and that the instability is so powerful that the water in the cooler outside would become unstable on a timescale of about 10 to the minus 30 seconds. Okay, so that's obviously wrong. And that's all got to do with the presence of this 4 acceleration term. So the solution, which Israel and Stewart introduced for a non-magnetized fluid, is to promote this scalar, the heat flux, parallel to the field, and this scalar, the pressure anisotropy, to dependent variables, which are then evolved alongside the other fluid variables, and to allow these, this conductive heat flux and pressure anisotropy to relax to the values specified in a naive theory. Okay, so that's what the evolution equations do. So we get a set of evolution equations out of this, and we have the same set of 5 conservation equations for rest mass, energy, and momentum, the same set of 3 evolution equations for the 3 components of the magnetic field, and then 2 additional equations are required to evolve the 2 new dependent variables, which are Q and delta P. And those are almost just simple relaxation equations that bring these quantities to the naive values on the, which I've written down here. I can explain what these are in questions if anybody wants to ask. But anyway, these relax the heat flux and the pressure anisotropy to the naive values on some time scale, which is really the heart of this, the specification of that time scale is the heart of this theory. It's the novel element, where we're arguing that the relaxation occurs due to kinetic instabilities in the plasma, and we're arguing that we understand something about the evolution of those kinetic instabilities. So those are the closure relations and the relaxation timescale that are specified by our understanding of saturation of kinetic instabilities in a collisionless plasma. Okay, so we've written a code to do this. Actually, Mani Chandra has written a code, and Francois Foucault, who's a postdoc at Berkeley. And it builds on top of the ideal GRMHD codes, and then includes these 2 new evolution equations for heat flux and pressure anisotropy. And the novel feature here, numerically, the new challenge, is that the right-hand side of these equations, this Q naught and delta P naught, contain both space and time derivatives. So it's not trivial to evolve these systems. And what we have to do is move the time derivatives to the other side of the equations, and then use a locally implicit scheme to step those pieces forward in time. So we have a new algorithm with a combination of implicit and explicit evolution. Okay, so let me just show you something about what this does in a test problem. So we set up a periodic box with constant pressure, and then put a slight temperature excess in a cylinder in the middle of the box. And on top of that, we place some magnetic field lines, which are shown by these light blue wavy lines. So these lines correspond to a field with very low pressure. So beta is much, much larger than 1. And so they don't evolve. They simply guide the conduction. And they sit there snaking back and forth across the grid. So we let it go. And you can see that the temperature diffuses, that the heat diffuses along those oscillating field lines, eventually bringing the entire system into equilibrium along individual field lines. Okay. So it's also possible to run axisymmetric models of accreting black holes with this code. And that was what was done in a paper with Francois Foucault. And I'm not going to spend much time on this, except to note that these evolutions are possible now, but they're incredibly expensive. So this is another factor of several more expensive than ideal relativistic MHD. Okay, and that is it. I have a list of further reading for you. A really inspirational paper for me was Komisarov's 1999 paper on numerical methods for special relativistic MHD. And it's extremely clear. We have a paper on our numerical scheme for general relativistic MHD. You can draw your own conclusions about the clarity of that. There's a book by Anil, who is really a mathematician on relativistic fluids, but there are certain fundamental results. For example, eigenvalues and eigenvectors, which are given in this book, which may be useful for you. There's a living review, a set of living reviews. A wonderful book by Luciano Rizzola and Olindo on relativistic hydrodynamics. And then there's a recent paper by Chris White on an extension of Athena++ to general relativistic MHD, which describes implementation of a much more sophisticated solver in a general relativistic context. Okay, that's it. Thank you.